Welcome back to our last video on basis, dimension, and column space. So that's 4.6 and I believe either 4.7 or 4.8. I'm giving you four matrices to look at, A, B, C, and D, and 6 questions to answer. Okay, and the same 6 questions for each matrix. We're going to do 3 of them. I'm going to leave it as an exercise for you to do the fourth. So, before I get there, let's look at matrix A. Okay, the questions that we're going to be answering is are the columns of matrix A independent? So when you do that, the question that you're answering is there a pivot in every column? Okay, and their answer is no. There's not a pivot in every column, so the columns are not independent. Okay, in fact, columns 2 and 3, so that's this vector right here and this vector right here are in some way related to vectors 1 and 4. And actually, it's easy to see that it's related to vector 1. So no, the columns of A are not independent. Does A span Rn? Okay, well, what is Rn? Well, let's look. A is a 4 by 4 matrix. Okay, so when we multiply A by some vector x, the vector x that we're multiplying it by is a 4 by 1 vector, and it's outputting some vector b, and that vector b is a 4 by 1 matrix. So what is our n? N is 4. So does matrix A span R4? And the answer is no. It doesn't span R4 because not every row has a pivot. Okay, you see rows 3 and rows 4 don't have pivots, so therefore it's not spanning R4. What is the basis for the the basis for the null space of A? Okay, for null A, this is going to require a little bit of work. So I'm going to pull out a scratch piece of paper. What we're going to do is we're going to look in the reduced row echelon form, and we're going to find all columns that don't have a pivot. So x2 doesn't and x3 doesn't. So that means in the set of vectors that are in the column space, the null space of A, x2 and x3 can be anything you choose it to be. x4 has a pivot. It's right there. So x4 must be equal to 0, and x1 must be equal to minus 2x2 plus x3. Okay, again, I'm setting this equal to 0. The augmented column is not there because it doesn't need to be there because we know that 0 is going to be on the other side. And so we can say that any vector that's in the null space of A is a vector that's going to look like this, where 0 is going to be in the fourth component. x2 and x3 can be any numbers they please, so long as x1 is minus x2 plus x3. So reworking this, we can write this as a linear combination of two vectors. A scalar times the vector negative 2, 1, 0, 0, plus a scalar x3 times 1, 0, 1, 0. So any linear combination of these two vectors is going to produce a vector like this. And any vector like this, when multiplied by the matrix A, outputs the 0 vector. So these two vectors form a basis for the null space of A. So the answer to this question here, the basis of the null space of A, is going to be the vectors negative 2, 1, 0, 0, and the vector 1, 0, 1, 0. And the answer to that is going to help us solve the fifth question. Okay, what is the dimension of the null space of A? Well, how many vectors form a basis for the null space of A? That's 2, so the answer here is 2. Lastly, the column space of A. Okay, so when you look at column space, what you're doing is you're looking at the columns where there's a pivot. Okay, so there's a pivot in column 1, there's a pivot in column 4. Okay, there aren't pivots in column 2 and 3, so they aren't needed. They are redundant, so they do not add to the span of the columns of the matrix. Therefore, the only columns that do add to the span are columns 1 and 4, and that's the vector 1, 3, 1, 5. It's column 1, and 3, 5, negative 1, 7. And so that is the basis for our column space of the matrix. And there are two vectors in it. Sorry, I gotta scoot this in here. There are two vectors in the basis, so that means the dimension of our column space is 2. Remember, dimension of column space, another way of saying was that it was the rank of the matrix. Good, good, good. Let's move on to matrix C. Okay, so you have 4, 0, 6, negative 2, 0, 10, 5, 5, and 3, 13, 2, and 10. Okay, go through the same list. Are the columns independent? Okay, well, is there a pivot in every column? The answer is yes. So the columns of this matrix are linearly independent. Does it span Rn? Well, what is Rn in this case? We'll answer the same question. 4 by 3. So C is a 4 by 3 matrix. You're multiplying it by some vector x and outputting some vector. What is the vector x you're multiplying it by? 3 by 1. And what are you outputting? You're outputting a 4 by 1. Okay, so does it span all of Rn? Okay, well, the space that you're mapping into, okay, that you're multiplying the vectors by, is this space right here. Is the one that B is in, and B is a 4-dimensional vector. So does it span all of R4? You look. Does every row have a pivot in it? No, every row doesn't have a pivot in it, so it doesn't span R4. It will span a 3-dimensional subspace of R4, but it doesn't span all of R4. What about a basis for the null space of A? Okay, well, null space requires us to do a little bit of work. So let's get rid of this and move this over. So we look at the reduced row echelon form. Okay, there's 3 elements in the vector, x1, x2, x3. Each one of them have a pivot. So x3 is equal to 0, x2 is equal to 0, x1 is equal to 0. And so the null space of the matrix, null space of C, is equal to one vector. It's the 0 vector. Okay, so basis for the null space of C is the 0 vector. So let's write that down. So we have a 0-dimensional null space. That's the answer to part E. What about the column space? Okay, the column space, every column has a vector in it, or a pivot in it. So all the corresponding vectors in the matrix C, the columns of C, are form a basis for the column space of A. So that is, make sure I can still, no, I'm barely in the screen. So that means the basis for the column space of A is 4, 0, 6, negative 2, 0, 10, 5, and 5, and 3, 13, 2, and 10. Okay, what is the dimension for the column space of C? That is the rank. Rank of that is 3. Okay, and what you do want to confirm is that the sum of the dimension of the null space and the column space, 2 plus 2, is equal to the number of components in, I want to call it your domain, but the vector you're multiplying the matrix A by. Okay, so 2 plus 2 is 4, 3 plus 0 is 3. Okay, so that's our dimension equation that I referenced in the last part of the video on video 16b. For matrix D, okay, matrix D is a 3 by 4. So we are going to be multiplying matrix D by a 4 by 1 vector, and we're going to be outputting a 3 by 1 vector. Okay, so we're mapping vectors in R4 to vectors in R3. Okay, are the columns of D independent? Does every column have a pivot? And the answer is no. Does every, the span of Rn, okay, so in this case, we're looking at the span of R3, okay? So does every pivot have a row? And the answer is yes. Sorry, does every row have a pivot? The answer is yes, so it does span all of R3. Okay, what about a basis for the null space? Okay, we pull out a scratch piece of paper again. Okay, look at the viewing window. Make sure you can, I'm writing in an area where you can see. You look at the reduced row echelon form for the matrix D. So you get, what, x2 to be free, x3 has to be 0, x4 has to be 0, x1 has to be 3 times x2. So the null space of the matrix D is the set of all vectors that take this form. Last component is 0, the third component is 0, x2 is whatever, and x1 is 3 times the second component. So that's going to be the set of all vectors that are scalar multiples of 3, 1, 0, 0. So we have the dimension of, we have the basis for the null space. The null space of matrix D is all linear combinations, which amounts to scalar multiples of the vector 3, 1, 0, 0. And the dimension of our null space, it's 1. The dimension of the column space. So columns 1, 3, and 4 all have pivots. So the column space of D is the vectors 1, 0, negative 4, negative 3, 0, and 12, and 0, 8, and negative 9. And how many vectors are in the basis for the column space of D? 3. And does our dimension equation work? Is 3 plus 1 the same as the number of components in X? The answer is yes. Very good. All right. So there goes that. Now, in these 3 examples, okay, I put a matrix in row echelon form. It doesn't need to be reduced row echelon form to answer the questions that I have. And the questions that I have are guiding you towards the dimension equation. Okay, so as you look at this matrix right here, what is the dimension of the column space of this matrix? Well, how many pivots are there? There's 2. Okay, so the answer to A is 2. What is the dimension of the null space? Well, how many free variables are there? 1, 2, 3. So the dimension of the null space is 3. Okay, what is the relationship between the dimension of the column space, that's the 2 pivots, and the number of pivots in the row echelon form of the matrix? Well, the answer is they're the same. Okay, the dimension of the column space. Make sure I'm pointing at something. I'm not pointing at something in there. The dimension of the column space is the same as the number of pivots in your matrix. Letter D. what is the relationship between the dimension of the null space of the matrix and the number of pivots in the row echelon form of the matrix? Okay, well, the dimension of the null space is going to be the difference of the vector, the number of components you'd multiply the matrix by. So in this case, what would you have to multiply this 4 by 5 matrix by? Well, you'd have to multiply it by a 5 by 1. And the number of pivots. So you'd have to multiply this by a 5 by 1 matrix. There's 2 pivots in here. The dimension of the null space is 3. Okay, the same number of columns for which there is no pivot. Okay, and the relationship between the dimension of the null space and the rank of the matrix, that's our dimension equation. The dimension of the null space plus the rank, the dimension of the column space, is equal to n, the dimension of the vector that you're multiplying the matrix by. Right? I give you 2 more examples right here. What you'll want to do, and I'll let you do that on your own, is to verify that the answer to these questions right here are the same for this matrix and this matrix, all in row echelon form. All right, so long section, very important, ties together a lot of the topics that we've been talking about in chapter 4. So please let me know if you have any questions. I'm, again, more than happy to help during office hours. I hope all's going well.